Newton's laws of motion. So let's talk about Newton's first law, also known as the law of inertia. The law of inertia says that objects that are at rest stay at rest, and objects that are in motion stay in motion, unless they're acted upon by an unbalanced force. Inertia is an object's tendency to resist its change in motion. So in other words, objects at rest will stay at rest. Objects in motion will stay in motion. Inertia only depends on mass. The more mass an object has, the more inertia it's going to have. Down here we can see a GIF where we have a guy driving a car. This guy is in motion. He hits a brick wall and he continues to be in motion, doing several front flips over that wall. The reason the guy is moving forward is because he was not wearing a seatbelt, so his body will continue to move forward. Let's talk about objects at equilibrium. Newton's first law predicts the behavior of objects for which forces are balanced. When forces are balanced, we say that objects are at equilibrium. An example of that can be when we are not moving or we are moving at a constant velocity. Both of those are objects at equilibrium with balanced forces. Another example is saying that there is no acceleration, which makes sense because if we're moving at a constant velocity, we cannot be accelerating. And like we said before, all forces are balanced in equilibrium. Therefore, the net force, or in other words, the total forces acting on that object, is zero. And when we say net force, we mean that we might have some forces acting up and some forces acting down. If we were to add those up, saying that the upward direction is positive and the downward direction is negative, they would end up equaling zero.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you're coming in and making that tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and/or speed.
So imagine that a quarterback is just taking a snap from the center, and a lineman gets free from the opposing team that's coming from the other side, and when they collide, you could see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight. Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
So for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on a quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall, and you just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron.
Let's talk about Newton's third law of motion now. Newton's third law of motion says, for every action, there's an equal and opposite reaction. This means that every single action that is occurring, there is another action that is also occurring in the opposite direction. So when we say that there's an equal and opposite reaction, we basically mean that there are two forces taking place that are both equal to each other. One is pointed in one direction and the other is pointed in the opposite direction. So let's say this is our action. We have a force pointed to the right. Well, we would have another force pointed back at it to the left, being the reaction. We can see that these two forces are the same size because their arrows are the same size, meaning that they have equal force. We can also see that they're pointed in opposite directions. Forces are going to occur in pairs. And like we said before, we would have an action-reaction pair. In this case, our red arrow is our reaction, and our green arrow is our action. This is the reason why force normal is equal to force gravity when we're on a flat surface. Let's take a look at an example here, where to the right we have a picture of a bat. The action force is the ball pushing the bat to the right. The reaction force, though, is the bat pushing the ball to the left. Equal forces, opposite direction. One is to the right and the other is to the left. Let's take a look at a few more examples here. And we want to figure out what are the action and reaction pairs in the picture below. On the left side, we have a baseball player with a mitt and a ball. I see that a ball is pushing this mitt to the left. So my action force is going to be ball pushes mitt to the left. My reaction force is just the opposite. The mitt is pushing the ball to the right. Let's look at our example to the right now. Again, we have a ball pushing a pin to the right. And then we have the pin pushing back on the ball to the left. For the baseball and the mitt example, the forces are going to be equal. So the force of the baseball is equal to the force of the mitt. And for our bowling ball, the force of the bowling ball is going to be equal to the force of the pin. Again, Newton's third law says equal forces, opposite direction. It doesn't matter what the two examples are, as long as those two objects are in contact with each other, they're both exerting equal forces onto each other. The only difference is that those forces are in opposite directions. Summarizing what we just talked about, inertia is telling us that objects will continue to do whatever it is they're doing. So objects at rest will stay at rest, and objects in motion will stay in motion. Newton's third law is just telling us that every action has an equal and opposite reaction. Basically, that's just telling us that forces occur in pairs. Those forces that occur in pairs have the same force value. The only thing that's different is the direction that that force is pointing in. and they're pointed in opposite directions. So again, if this is one of my forces, this is my action force, and let's say that this action force is 50 newtons, I would have a reaction force pointed in the opposite direction with the same magnitude of force. No matter what the example is, we need to remember that those forces are always equal and opposite. So if I gave you an example saying that you were driving your car down the street and a bug hit your windshield, who felt a greater force, the bug or the windshield? A lot of people get this question wrong and they say, well, clearly the windshield. Look at what happened to the fly. That's not right. The fly and the windshield are feeling the exact same force. The reason they feel the same force? Newton's third law. The reason the bug goes splat? Well, you'll have to wait for next time when we talk about Newton's second law.